A frequently asked question in Monte Carlo simulation is how many iterations are necessary to obtain precise and stable results? The answer is not straightforward and depends on several factors, including the required precision, the computational capacity, and the nature of the model. In this lesson, we will explore how to determine the optimal number of iterations, balancing accuracy and computational efficiency. The relationship between iterations and execution time: the higher the number of iterations, the longer the processing time. In this particular model, testing 9 sets of iterations, ranging from 100 to 50,000 iterations, processing time increased linearly with the number of iterations. For example, for 100 iterations, it took 8 seconds. For 50,000 iterations, it required 2,600 seconds. The observed processing speed between 13 and 24 iterations per second were generated regardless of the dataset size. This indicates that simulation time grows proportionally with the number of iterations. Now, there's a number of factors determining the number of iterations. The optimal number of iterations depends on various factors such as the model complexity, number of variables and relationships, type of distributions used, symmetric versus asymmetric, the presence of correlations between variables, and the level of precision required in results. As the number of iterations increases, the precision improves, reducing the variability of the results. The convergence stabilizes. That means that the values stop changing significantly. When does this stability occur? For the mean, the average of the data, after 5,000 iterations, the mean begins to stabilize and changes very little with additional iterations. Upper percentiles, extreme values of the distribution. In the 95th percentile, for example, values still fluctuate with fewer than 1,000 iterations. Between 5,000 and 10,000 iterations are needed for the percentile to converge and stabilize. So our practical recommendation on how many iterations to use: the general rule: for most simulations, a range between 5,000 and 10,000 iterations is sufficient to achieve convergence and stability without unnecessarily increasing the processing time. Observe, for example, this sequence of 9 histograms generated with an increasing number of iterations, showing how the convergence or stability of the responses consolidated by the Monte Carlo simulation process improves. This series of graphs is generated with 100, 200, 500, 1,000, 2,000, 5,000, 10,000, 20,000, and finally 50,000 iterations. With 1,000 iterations, histograms still appear fragmented and poorly defined. With 10,000 iterations, histograms smooth out and converge, indicating better statistical representation. So we conclude, the higher the number of iterations, the higher the precision, but also the longer the simulation time. After 5,000 iterations, mostly, results begin to stabilize with minor changes beyond 10,000 iterations. Percentiles require more iterations than the mean to converge. For most models, then, between 5,000 and 10,000 iterations is an optimal balance between precision and computational efficiency. So, our final recommendation: if computational capacity allows, using 10,000 iterations will ensure stable results without excessively increasing simulation time.